Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. My name is Mohamad Zahin bin Mohamad Zahir.
My name is Ahmad Fikri bin Dahari.
My name is Mohamad Adib bin Zulkifli.
And today we will present to you on our first assignment in the subject of Power System Engineering in the title of HVDC and FACTS. Okay, so for in the introduction, global electricity consumption nowadays has continued to go up rapidly at a rate faster than energy consumption. The demand for electricity is set to increase further as a result of rising household incomes with the electrification of transport and heat, and growing demand for digital connected devices and air conditioning. As you can see in the graph shown there, global electricity demand by region in the stated policy scenario of 2000 until 2040 shows an upward trend and increasing trend. In the stated policy scenario, global electricity demand grows at 2.1% per year to 2040, which is twice the rate of the primary energy demand. Electricity demand growth is said to be particularly strong in developing economies. Government policies, market conditions, and available technologies collectively set a course for electricity supply to shift towards low carbon sources, as you can see in the graphs shown. In the sustainable development scenario, electricity is one of the few energy sources that sees growing consumption in 2040, mainly due to electric vehicles alongside the direct use of renewables and hydrogen. Accelerated efforts on renewables, nuclear power and carbon capture technologies rapidly decarbonize electricity supply, compensating for the sharp decline of coal-fired power generation and reducing the power sector of CO2 emissions by 3/4 by 2040. However, during this COVID-19 pandemic, electricity demand dropped to Sunday levels under lockdown, with dramatic reductions in services and industry only partially offset by higher residential use. When confinement was eased in Italy and Germany in April 2020, electricity demand showed the first signs of recovering. This trend was confirmed in May as more countries such as India, France, Spain, Great Britain softened lockdown measures. In several Europe countries, lockdown periods have seen new highs in variable renewables contribution as a share of electricity demand. In Malaysia, the TNB has said in the Star newspaper, during the MCO, electricity usage in the industrial and commercial sectors dropped between 25% and 50% as businesses and industries halted activities, while usage in the residential sector surged between 20% and 50% as families stay indoor and employees work from home. According to the International Energy Agency, IEA, renewable was the only source that posted a growth in demand driven by larger installed capacity and priority dispatch. So coming back to the fact that the electricity will be surely increase in the future, thus the smart transmission system is a must to be developed further, as the situation will make the power system much more complex. Electricity network is one of the largest, most complicated and most sophisticated systems in the world, and electricity grid has to be smart enough to be able to handle thousands of generators of different technologies and sizes, as well as supplying electricity of millions of customers in a reliable and sustainable way. Innovative solutions with HVDC, high voltage direct current, and FACTS flexible AC transmission systems technology play an important role in the smart transmission to enable bulk power long distance transmissions and great access of renewable energy sources RES to reduce the transmission losses and CO2 emissions, to interconnect countries and even continents for an open electricity market, and to improve the transmission stability.
Okay, let's get into the HVDC, which is high voltage direct current system. So for the overview, the HVDC technology is used in transmission system to transmit electric bulk power over long distance by cable or overhead lines. It is also used to interconnect asynchronous AC systems having the same or different frequency. For the terminology, the following terms are found found necessary to define for the following section of the paper. Figure 1 can be used as a guide. It shows a schematic of the overall system perspective of a general HVDC system transferring electric energy from one AC system or not to another in any direction. Okay, for in-depth explanation, the HVDC system contains the converter stations and the transmission lines or cables. The HVDC converter station or HVDC station includes the AV switchyard, the converter transformer system, and the converters and the auxiliary subsystems in the station. The valves are located in the converters and consist of a number of thyristors or transistors, depending on HVDC technology that are connected in series. Converter transformer system (CTS) is the arrangement of converter transformer are connected to the valves. CSC HVDC is the technology where lines commutated current source converter (CSC) is used. The company trademarks as HVDC Classic, ABB, or simply HVDC. VSC HVDC use the voltage source converters VCS as its core components to convert AC to DC and vice versa. The company trademark HVDC Plus, Siemens, HVDC Lights, ABB, or VSC HVDC. So next, the connections and operating principle. HVDC configurations depending on the application and location. A number of different HVDC station configuration can be identified. In this paper, these are presented for CSC HVDC with CSC converter symbols, but similar configuration setups exist for VSC HVDC. These are three basic HVDC configurations with different converter arrangements. Figure 3 shows three basic HVDC configuration with different converter arrangements. So for the first one, back-to-back configuration. Figure 3A shows a block diagram of the back-to-back configuration with a 12 pulse configuration. Secondly, monopolar configuration. A monopolar configuration with a 12 pulse configuration is shown in figure 3D. The configuration is mainly used in undersea transmission. And the third one is bipolar configuration. The bipolar configuration can be seen as two monopolar configurations in parallel with a positive and negative pole. Figure 3C shows a block diagram of the 12 pulse bipolar configuration. And lastly, for the advantages, an important advantage of HVDC is that it can be applied in cases where an AC interconnection is not possible because of technical problems. It offers technical and economical benefits, such as lower line costs, no need for common frequency control, stable operation even with a low power interconnection, and improved dynamic condition in AC system. So let's look for the case study of HVDC system. For the case study, we choose Caithness Moray project, which is located at Scotland. The Caithness Moray HVDC project CM project is the first HVDC scheme in the north of Scotland and represent a 1.1 billion capital investment by SHE Transmission in the electricity network. The first phase of the project links Petal in Caithness and the Black Hillock in Moray with plus minus 320 kilovolt, 113 kilometer submarine HVDC cable. However, the scheme is designed as a 3, 4 or 5 multi-terminal scheme, allowing for future extension to connect the Shetland Isles and other renewable generation. The Caithness Moray HVDC project is a landmark project for developing the electricity network in Great Britain toward a low carbon network. Most specifically, the CM project enables the export of electricity from one of the most productive renewables areas in Europe. It's the first multi-terminal design project in Europe and demonstrates how a multi-terminal grid can be developed without a use of HVDC breakers. However, it is also a technically challenging project. Connecting to a weak AC 275 kilovolt network in the north of Scotland, designed for multi-terminal operation and potential for multi-vendor extension. The HVDC Center was able to help address these challenges and assure for delivery of this project through the use of replicas of the control panels to test the operation of the system under a range of conditions with a detailed representation for a SC network. Furthermore, as the CM scheme is extended to multi-terminal operation, the HVDC Center will have a pivotal role ensuring the operation of the complex multi-terminal controls using replicas of all three terminals.
So next, for the facts, which is flexible AC transmission system. So for the overview, IEE defines facts as alternating current transmission system, incorporating power electronic base and other static controllers to enhance control ability and power transfer ability. So the main purpose of the FAC is to supply the network as quickly as possible with inductive or capacitive reactive power that is adapt to its particular requirement, while also improving transmission quality and the efficiency of the power transmission system. Okay, so type of FACS controller, there is four types of FACS controller. The first one is the series controllers, which is the function is to reduce the inductivity of the line and introduce voltage in series with the line. The example is SSSC, TCSC, and TSSC. So for the next one is the shunt controller. The function is to reduce the capacity of the transmission lines and introduce the current in series with the line. The example is the STATCOM, TSR, and TSC, and SVC. For the next one is the combination of the two from the above, which is shunt series and the series controller. So for the shunt series is to introduce current in series using the series controllers and voltage in shunt using the shunt controllers. So for the series controller, it's a combination of the series controllers providing series compensation and transfer real power. So this is the list of the FACS controller. For transmission lines, we have SVC, STATCOM, TCSC, SSSC, TCPER, and UPFC. There is FACS also used for another special application, which is NGH, SMES, TCBR, TCVL, and current limiter. So for the operating principle of FACS, so by the equation above, U is the voltage at the end of the transmission, while S is the equivalent impedance of the transmission, and sigma is the phase angle difference between the both systems. So as the equation above, transmitted power is influenced by the voltage, impedance, and phase angle, and FACS device can influence one or more of these parameters. So in order to understand more, so we can look at this example of the application of FACS in a long distance. So the situation is power is transmitted from subsystem A to subsystem B over the distance of 1000 km. So they're using of 70% of feed series compensation and 17% feeds shunt compensation, and assuming a single line fault with a disconnection of the faulty line section. So there is a faulty line there. So the system is actually at the limit of stability when transmitting 1700 megawatt. So if the power are more than 700 megawatts, it will be it will be unstable. So we can see that on the trace one, which is the first graph there. So the application of the FACS can makes the power can be transmitted over 1700 megawatts. So let's look at the SVC. So there is SVC there. So additional SVC rated 180 MVR keeps the system stable even at a transmitted power of 2500 megawatts. So we can see that at the trace 2, which is it's a stable graph. So at a trace 4 also there is the using of the application of TCSC, and the graph also stable. So at the trace 5 is also an application of the TCSC, which the variation of the line impedance. This is the advantages of FACS. So the first one is the environmental benefits, which reduce the needs for adding new additional transmission lines. So the next one is increased stability, which increase the transfer capabilities and reduce risks of line trips. So the next one is increased quality of supply. Since industry needs high quality of electricity supply, FACS can provide that. So flexibility and uptime. So installation of FACS actually can not that long. So the requirement is 12 to 18 months and require only small land area. So for the financial benefits, improve stability in power system can reduce risk of host outage, that can reduce risk of lost revenue and penalties from power contracts. And the last one is reduce maintenance costs. The maintenance cost for the FACS is minimum. Plus, with using FACS for the transmission system, the number of lamps is minimized, thus the maintenance cost reduced. So for the case study of thyristor controlled series compensator at Brazil, so it start operate on 1090 and 99, located at Imperatriz, northern end of the power corridor, connecting two systems which previously not interconnected. So both AC and DC are actually being tested, and it's in favor of AC option. So consists of a single 500 kV compact circuit, subsequently double, more than 1,000 km long, and series compensation in several places along the lines. The power transmission capability is 1,300 megawatts. The task for this FACS is to damping low frequency inter-area power oscillation between the power system on either side of the interconnection. So the oscillation of 1.2 Hz could be a hazard to power system stability, affecting power transmission capability. So the TCSC fix that.
Conclusion, following the increasing trend of electricity demand, the smart transmission system must be applied, as the system will surely be much more complex as the development efforts of this age and day are rapidly moving forward. The electricity grid must be intelligent enough to handle thousands of generators of various technologies and sizes, while also reliably and sustainably supplying electricity to millions of users. FACS controllers are now considered a proven and mature technology. The FACS technology can reliably respond to the dynamic variation in the electric power arising from changes in load or amount and quality of power generated. With the HVDC systems, the power flow can be controlled rapidly and accurately as to both power level and direction. Using HVDC to interconnect to points in a power grid in many cases is the best economic alternative. The HVDC technology is used to transmit electricity over long distances by overhead transmission lines or submarine cables. HVDC over land links are usually bipolar and or on overhead lines. Compared to AC, DC transmission has several advantages. So this is the list of our reference, which consists of a total 7, 8, 9, 10, 11, 12. So this is our references, which consists a total of 12 citation references. So that's all from us. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.